This is a video lecture over the process of stoichiometry and how to set up and solve stoichiometry problems using a balanced chemical equation. So your notes introduce you to the idea of what stoichiometry is, and we talked about this last class, that it's a very real-world part of chemistry in many companies that are out there that have any type of a chemical product. They have to be able to do this process to not only determine how much product to make, but the amount of the reactants or the ingredients that go into making that product. So all of this is based on the law of conservation of mass. We know that when we balance equations, it's because whatever goes into that reaction has to also come out, mass-wise. So the law of conservation of mass tells us that the mass of the reactants is equal to the mass of the products. And there's a couple of things that we're going to use this stoichiometry process for. We're going to not only use it to calculate the mass of substances produced from a certain amount of reactant, but if we want to make a certain amount of product, we can work backwards and figure out how much of a reactant we would need to do that. So there's a lot of ways to use stoichiometry. As long as you have that recipe, that balanced equation to start with, you can really find out the amounts of anything else that's part of that balanced reaction. Back in the first semester, we learned how to do conversions from moles to grams and from grams to moles, and we even practiced that a little bit last class with a sample problem. And we used the mole and molar mass to do that. We find molar mass of any element or compound using the periodic table. So we reviewed that a little bit last class with a practice problem. Most stoichiometry problems you're going to solve will involve a conversion from mass to moles or from moles back to mass. Now what we're going to talk about too is something called the mole-to-mole ratio. When we balance a chemical equation, we use coefficients. Those are the numbers that are in front of each part of the equation, and we use those coefficients to help us balance the equation. Those coefficients represent the ratio of all the parts of a chemical equation to everything else that's in that equation. We call that a mole ratio as well. So just to get a little practice with using mole-to-mole ratios and being able to pick them out from a balanced equation, let's go ahead and talk through these first two questions, example 1 and 2. And it's just having us actually write down that ratio. And we want to write it down in the form of a fraction because that's what's going to look like when we actually set up our stoichiometry problems. So it's giving us a pretty common equation, and it is the synthesis of ammonia. So we have nitrogen and hydrogen giving us ammonia. And we want to pick out from this reaction the mole-to-mole ratios that it's asking us to find at A, B, and C. So letter A is asking us to find the mole-to-mole ratio between nitrogen and hydrogen gas. So if you look at the coefficients, for nitrogen there is an understood 1 there, and then hydrogen has a coefficient of 3. So the ratio of those two reactants to each other in this balanced equation is 1 to 3. Okay, and we would write it like a fraction. For letter B, it's nitrogen to ammonia. The ratio of a nitrogen to ammonia using the coefficients is 1 to 2. And then finally, hydrogen to ammonia is 3 to 2. Okay, so it's simply using those coefficients to write what's going to ultimately be a conversion factor for us, but writing these fractions that represent mole-to-mole ratios. Okay, on problem number 2, it's the same idea. It wants the mole-to-mole ratio of hydrogen to dihydrogen sulfide. So hydrogen's coefficient is 8, dihydrogen sulfide's coefficient is also 8. So I could either write 8 over 8, or if I want to reduce it to work with easier numbers, I could write 1 over 1. Hydrogen to sulfur is 8 to 1. And finally, dihydrogen sulfide to sulfur is 8 to 1 as well. Okay, so those are called mole to mole ratios, and anytime that we need to find that, we're going to use our balanced equation and use the coefficients that are in front of either the reactants or the products, whichever two things are involved in the ratio. Now, we can actually use that mole to mole ratio, that fraction, as a conversion factor, and we're going to do just simple mole to mole conversions. Ultimately, we're going to be able to start with the mass of one substance and convert it to the mass of another substance from a balanced chemical equation. And we did do a problem like this last class. It was an example problem before you were able to actually eat your s'more that you made in class. You had to kind of show me that you could set up and solve a problem that was a mass to mass conversion. So you have actually seen that before, but we're going to kind of back up a little bit today and kind of go through the steps of how we get to that. So question number 3 says, answer the following questions for this equation, and it gives us the synthesis of water. It's first asking us what is the hydrogen to water molar ratio. So I'm going to look at hydrogen's coefficient and water's coefficient, and I'm going to write a fraction for that. It is 2 to 2. I'm going to go ahead and reduce it and put 1 to 1 because that's the easiest numbers that I can think of to work with. And then it's asking me some questions applying that ratio. If I have 20 moles of hydrogen gas on hand and plenty of oxygen, how many moles of water could I make? Well, I'm going to write down my given, 20 moles, and I'm going to write what it is of that I have 20 moles, and that's hydrogen gas. Okay, so that's my given, and I want to know how many moles of water I can make. So I can do a simple one-step conversion, and I know that you could probably do this in your head, but this is more about understanding the process of how to set it up because the questions get to be more complex. But we're starting with 20 moles of hydrogen, and I want to set up a conversion factor, my mole to mole ratio, so that I can cancel out moles of hydrogen and be left with moles of water. So my ratio of moles of hydrogen to moles of water, 1 mole of hydrogen. And I'm putting that on the bottom so that moles of hydrogen will cancel. Can make 2 moles, or sorry, my ratio is 1 to 1, 1 mole of water. Now I don't need a graphing calculator or a calculator at all to actually figure this out. Since they're in a 1 to 1 ratio, I know that if I have a certain amount mole-wise of hydrogen, I'm going to make that same amount of water. So the answer to that question is 20 moles of water. Okay. The letter C says, what is the oxygen to water molar ratio? Oxygen to water is 1 to 2. So I'm going to write my fraction 1 to 2. If I have 20 moles of oxygen and enough hydrogen, how many moles of water can I make? Well, if I go to set this up, it looks like this for my conversion factor. 20 moles of oxygen. Okay, and my mole to mole ratio is 1 to 2. I want to put the number, the coefficient number that goes with oxygen on the bottom. 1 mole of oxygen. Okay, and I want to put the ratio or the coefficient for water on the top of this conversion factor because that's what I want to end up with. 2 moles of water. My moles of oxygen cancel, and I can multiply across. 20 times 2 is 40 moles of hydrogen, or water, sorry. There we go. So I'm setting up ratios or conversion factors basically using the coefficients from my chemical equation, my balanced equation. That's the important part too. Okay. We are going to pause the recording for just a minute, and I want you to see if you can answer the questions for number 4. Similar questions as we did in number 3, but see if you can use your mole to mole ratio from this balanced equation to actually solve the problems. Okay, now that you have had a chance, hopefully, to work through A through D, under question number 4, you were able to set up and solve for each one of the parts of the equation that was asking for. And I realized that with the simple numbers in this particular question, or in each one of these particular questions, you could probably have done this in your head without setting up a complex conversion factor like this. But again, remember, it's about the process. I'm trying to show you, as your questions and numbers get to be more complicated, a pattern or a process that you can use, a strategy you can follow to set up and solve these problems. So basically what I'm showing you is a dimensional analysis approach where you take whatever given value you have in your problem, you put it in the top left box of your conversion setup, and then you're going to set up a mole-to-mole ratio where you put what you want to cancel out, the moles of what you want to go away on the bottom, so it cancels out, and the moles of whatever you're trying to find on the top of that conversion factor. So that way there's no guesswork involved as far as should I multiply, should I divide, which number. You simply stick to that balanced chemical equation and set up your conversion factor fraction correctly so that you're canceling out the moles that you're given, whatever substance you're given in the problem, and you are converting to whatever the moles are that you're trying to find of that particular substance. Okay, so in this set of notes, you have some steps that you can always refer back to help you set up and solve a stoichiometry problem. And this is when you're working from mass to mass conversions. And what that means is you're going to be given the mass of one of the substances in a balanced equation, and you're going to be asked to find the mass of something else in that equation. So you can do that using this process of stoichiometry as long as you have your recipe to start with, which is your balanced equation. So given to you are the steps to follow and to refer back to if you need them as you're trying to set up and solve these problems. So the very first thing you always need to have is your correct chemical equation. So formula writing, of course, is pretty important here because that makes for balancing the equation correctly, and we know that the coefficients represent the mole-to-mole ratios, and that's kind of the foundation, the whole idea behind this stoichiometric process. So you've got to balance your equation next. And then don't forget that it's the coefficients that represent your mole-to-mole ratio of reactants and products. Then you're going to look at your problem you're trying to solve for and figure out what it's asking you to find, what it's giving you and what it's asking you to find. So whenever you use dimensional analysis, you're always going to start with whatever quantity is given to you. Make sure that you're writing down the number and the units and the symbol of whatever it is that's given to you so that you keep track of what you're canceling out and what you're keeping in this whole dimensional analysis setup. The first step, if you're given grams, you're going to have to convert it to moles. You can't use the balanced equation unless you have moles of whatever it is you're talking about, because that's what those coefficients represent. They're mole ratios, not mass ratios. So you have to convert to moles first. This is really important. It's got to be in moles. Your given units have to be in moles before you can use the ratios from the balanced equation. And then you're going to continue setting up conversion factors until you end up with the units that you're looking for. Okay? You're definitely going to have to use a mole-to-mole ratio from your balanced equation because that's going to show you that relationship between what you're given and what you're trying to find. And don't ever forget, you're dealing with proportions. Okay, it's ratios. So if you know the moles of anything in that balanced equation, you can find the moles of anything else in that equation, whether it's a reactant or a product. You'll finish up solving the problem. And then if you have moles calculated, you can actually find mass. And then later we'll talk a little bit more about how to find particles. So that's where Avogadro's number is going to come into play. And then at a later unit, when we talk about gas laws and gases, we'll even talk about moles as far as liters go, because we'll talk about volume of gases. That's how we measure gases. But that'll come in a little bit later unit. So I've started you out with some practice problems that I want to show you how to set up. So I'm going to set up and solve the first one first, which makes sense. And then I am going to pause this video so that you can work the next two problems, and then you can come back and play the video and see how the last two problems in your notes are solved. Okay, so this very first stoichiometry problem, we want to kind of follow our steps and make sure that we're setting up and solving it correctly. Before we can ever solve anything stoichiometrically in this problem, we have to have a recipe for what this problem is describing, and that's our balanced chemical equation. So it says Mary performed a double displacement reaction, which is the same as double replacement, it's the same thing, of calcium chloride with silver nitrate. We know how to predict products, so we are able to set up, balance this equation. It is telling us that she was given 12 grams of calcium chloride, which is one of your reactants, and asked to predict the theoretical mass of calcium nitrate that would be produced. The reason it says theoretical is because it's not a perfect world, and there's no way she's going to ever get 100% of what she's supposed to get, because there's always some error involved in collecting the product. Okay, so the very first thing we have to do is write and balance the chemical equation, which serves as our recipe. So we have calcium chloride plus silver nitrate, and it's double replacement, so it's going to make calcium nitrate, and I want to write my formulas correctly, and silver chloride. Okay, so I want to go back and check to make sure that all of my compounds are written correctly before I balance the equation, and it looks like all of the parts of my equation are written correctly, and now I'm going to balance it. So I'm going to balance by adding a 2 here. I'm going to need 2 silvers. Now I have 2 chlorines and 1 calcium, so it's balanced. Now, it is asking, or it's giving me in the problem a mass amount of calcium chloride. And it's asking me to find calcium nitrate. So the two things in the problem or in this reaction that I'm going to be working with are calcium chloride and calcium nitrate. So at this point, once I know I have a completely balanced, correct chemical equation and I know what it's asking me to find, I can set up my dimensional analysis bracket. I'm going to take whatever's given to me in the problem and write it in the top left box. So I'm going to write 12. Don't forget to include your significant figures, 12.0 grams, and I'm going to write the formula for what it is that it is giving me, calcium chloride. Okay. Remember that the coefficients that are in front of every single part of this equation are mole coefficients. They represent mole-to-mole ratios, not mass-to-mass ratios. So I have to start by getting moles of whatever's given to me. It's giving me grams, so I need to convert that to moles. So I'm going to put 1 mole of calcium chloride on the top. And I'm going to look on the periodic table and I'm going to find the molar mass of calcium chloride. When I add up the mass of 1 calcium and 2 chlorines, I get 111 grams of calcium chloride. Okay. Well, that's going to let me cancel out grams. And now I have moles of calcium chloride, so I can now use the ratios from the balanced equation because that's what they represent, mole ratios. So I want to look at the ratio between calcium chloride and calcium nitrate. Well, it's a pretty easy ratio right now. It is 1:1. So 1 mole of calcium chloride is needed to make 1 mole of calcium nitrate. Okay, my moles of calcium chloride are going to cancel out, and it's getting me to my almost last step, my very last part of this problem, because it asked me to find the mass of calcium chloride, or sorry, calcium nitrate. So I've got moles of calcium nitrate, but I need the mass of it. That would be grams. So once again, I'm going to use the periodic table, and I'm going to find what 1 mole of calcium nitrate weighs. Okay, so when I look on the periodic table and I add up 1 calcium and 2 nitrogens and 6 oxygens, it gives me 164 grams. And that is the molar mass of calcium nitrate. And remember, when we take numbers from the periodic table, we make it a little easier on ourselves to round it to 3 significant figures. You can always use more than that, but never use less than 3 significant figures. Okay, when I cancel out my moles of calcium nitrate, I am left with what it asked me to find as far as units go. Grams of calcium nitrate, that's the mass. So I'm done with this problem, and I just have to do the math of it. So I'm going to multiply all the numbers across the top, get an answer. I'm going to multiply all the numbers across the bottom, get an answer. And then I'm going to divide. Okay, so when I multiply all the numbers across on the top, I get 1,968. And when I multiply all the numbers across on the bottom, I get 111. And when I divide those two numbers, rounded to 3 significant figures, because that's what the measured number from my problem had in it, I get 17.7 grams for my final answer. All right, I want you to try the next 2 problems on the same notes page, and then when you've attempted both problems and you have your work done, go ahead and restart the video so that you can see the worked out answer for those 2 practice problems. Okay, let's take a look at example number 2, or practice problem number 2. The balanced equation is given to you. It should look pretty familiar. This is cellular respiration. So it's taking glucose, and it's a combustion reaction, combining it with oxygen. It's making carbon dioxide and water, and it's already balanced for you. It is giving you a gram amount of glucose and asking you to find how much oxygen it's going to take to oxidize the glucose to carbon dioxide and water. So this particular problem is giving you a reactant and asking you how much of the other reactant you're going to need to react with that amount that's given completely. So, but I set it up the same way. I set up my conversion factor, and I put my given in this top left box, and I wrote the unit and the compound with it. I know that I can't use these ratios in the balanced equation unless I have moles as my units. So the very first thing I have to do is convert grams of glucose to moles of glucose. So that was my first conversion factor. Once I have converted to moles, then I can look at the ratio between those 2 parts of the question, what was given to me and what it was asking me to find. I put glucose's coefficient on the bottom, and I put oxygen's coefficient number on the top of my conversion factor, because I wanted the glucose to cancel out and I wanted to be left with moles of oxygen. Finally, I'm going to convert to grams because it asked me to calculate the number of grams of oxygen, and I know that 1 mole of oxygen, looking at the periodic table, since it's O2, oxygen's diatomic, it weighs 32 grams. Once I cancel out my moles of oxygen, I can now solve the math of the problem because I have the units that it asked me to find in the problem, which was the mass of oxygen. So I'm going to multiply all the numbers across on the top, which gave me 2,400, and I'm going to multiply the number across on the bottom, which was just 180. And when I divide it and rounded to 3 significant figures because of my measured number from the problem, I end up with 13.3 grams of oxygen. Okay, finally, the very last question. was single replacement reaction between aluminum and hydrochloric acid. So I wrote and balanced my equation so that I had my coefficients to work with when I get to that point. It was giving me aluminum and asking me to find hydrogen gas. So I put my given amount in the top left box along with the units and the substance that it gave me. And I need to convert to moles first, but because until I do that, I can't use these mole coefficients, these ratios. So I converted to moles using the molar mass of aluminum. And once I had moles, I can now use and set up my mole to mole ratio for my balanced equation. And I put 2 moles of aluminum on the bottom because the coefficient in front of aluminum is 2. And I put it on the bottom because I want aluminum to go away. And I want to be left with what it asked me to find, which was hydrogen. The coefficient for hydrogen is 3. So 3 moles of hydrogen gas can be made from 2 moles of aluminum, according to my recipe, this balanced equation. Finally, I need to get rid of moles because it asked me to find how many grams of hydrogen will be produced. Well, I can go from moles of hydrogen to grams of hydrogen by using hydrogen's molar mass. I know that 1 mole of hydrogen gas, which is diatomic, weighs 2.02 grams. So I cancel out the moles and I multiplied across on the top, multiplied across on the bottom, divided those 2 numbers and ended up with 1.04 grams of hydrogen gas.